Okay. Well, I hope you guys are doing well. I hope you are doing the homework and understanding the content covered in those problems. And not many students have been asking me questions, so I'm just assuming that you guys are learning and doing well. But if there's any problems, don't hesitate to ask or come by office hours or anything like that. I hope the video solutions for the homework are also available and or working out for you, and as well as the practice quizzes. So as we move on, today we're going to enter chapter 4, but I just kind of just want to give you maybe a small, well, you already took a quiz, but I also want to just kind of ask you a few questions here that are that capture more big picture concepts, which is a little bit harder to capture to put in a quiz. So I'm going to, I guess, write a couple questions up on the board. You can try to answer them in your head. Don't shout out the answer, and then I'll give you what my opinion of these answers are. Okay. So one question is, what does the standard deviation tell us? Okay. So don't shout out your answer, but write this down and see if you can answer this question yourself. What does the standard deviation tell us, or why do we bother calculating the standard deviation? What is a z-score? Okay, not what is the formula for the z-score, but why do we calculate a z-score? What is the purpose of a z-score, right? I'm going to just ask you also to list summary statistics for center and list summary statistics for spread. And then maybe the last question will be, how are summary statistics useful? Okay. So just some big picture questions. Kind of covering the stuff we covered last week in chapter 3. All right. Does someone want to volunteer an answer for the first question? What does the standard deviation tell us? Yeah.
Square root of the variation.
Okay, square root of the variation. All right. Maybe, so that is kind of the formula, but well, then why would we calculate the variation then? Yes, go ahead.
The average distance between each number?
Okay, average distance, I would say actually not between each number, but between each number and the mean. Okay. All right, so the big picture concept that I'm going for here is it tells us the spread in our data. It tells us if our numbers are alike or if they're quite different from each other. Okay, what does the standard deviation tell us? It tells us the spread in our data. The other, what the other students have mentioned, those are correct and valid. But in terms of just big picture things, what I'm going for is the standard deviation tells us the spread in our data, which is the concept of how similar or how different our data points are. And I guess one loose definition would be the quote unquote typical distance between each point and the mean. So if each point is similar to each other, then they would also be very close to the mean. If each point is quite different from each other, then they would be far from the mean. Any volunteers for what a z-score is? Yes, go ahead.
How close or how far a variable is from the average?
Okay, it's it's a distance a point is from the mean, but it's expressed not in just its units, but what? In standard deviations. So it's basically the distance a point is from the mean in standard deviations. Is from the mean or the average. Okay, and to get at this idea of what is the purpose of the z-score, and its purpose would then be to put measurements from different things on the same scale. Okay. So, you know, if there were two different people and they took two different exams, one person, maybe they score 40 points above average. Is 40 points above average good or bad? It depends on the scale, right? So if one person scores 40 points above average and another person scores 3 points above average, we don't quite know which one is more impressive. But if we say person A scored 1 standard deviation above the mean, where person B scored 2 standard deviations above the mean, then they are now on the same scale and we can make comparisons. Okay, so list some summary statistics for center. What do we have here? Yeah, the mean and the median. Okay, so these are ways to summarize the center. Summary stats for spread, what do we have? Range, good. What else? IQR, and I heard someone else say something. Variance, and it's very related, standard deviation. I pretty much say they're the same thing, just because one is directly just the square root of the other. So variance and standard deviation. And these are ways to measure spread. Okay. And how are summary statistics useful? Okay. Well, number one, they summarize lots of data into just a few key points. And what that then allows us is then to make quick comparisons between groups of data, okay? Sorry, let me, Okay, so just some big picture concepts there. And then, and with this, we'll move forward into chapter 4. Okay. Okay. So chapter 3 was all about summary statistics describing a set of data, a numeric variable, right? All of those things were for numeric variables. And in chapter 4, we're still going to describe data, except now we're looking at two numeric variables together. Describing two numeric variables that are related. Okay. Okay, and so you can imagine a data set. Okay, and each row is a case, right? And each column will be a variable. Okay. And we can collect, let's say, two numeric variables. And so this is well, I hope nobody hates, well, maybe some of you hate snakes, but I hope nobody opposes this, this example here, okay? So just imagine we went to, I don't know, the zoo, and they have a snake exhibit or something, okay? And I don't know, the snake farm or something, well, whatever. Just go along with me here, okay? And we look at this one snake pit. Okay, so we'll look at a snake pit, and we've got a bunch of snakes. We'll say they're mostly of the same species or whatever. Okay, or we'll just say the same species. All right. And so what we're going to do is we're going to measure how long each snake is. We can name them if you want, but we're gonna measure how long each snake is, and then we're gonna measure how much the snake weighs. Okay, so we'll measure the length, and we'll measure its weight. Okay, and so you got this is my drawing of a snake. And then, here's another snake. See, I'm really good at these drawings, okay? And then we go, oh, well, this is, this guy is whatever, 32 inches long. Okay, and he weighs, how much does this guy weigh? We'll say 6.2 pounds. I have no idea. I'm just making this stuff up, okay? It probably weighs more than that. But whatever. Okay. And so we're gonna keep track of these things, okay? So I'm completely making up these numbers. Okay, and so this guy, maybe he's only 20 5 inches long. And how much do you think he weighs? Okay, well, I'm going to just write 5.1 pounds. Who knows? Okay. I'm just making stuff up. And, you know, this was Sam the snake, and this is... what?
Jackson.
I was going to go for S names here. Simon. And, what? Sally. Okay. And so Sally is, 29 inches long and weighs 5.8 pounds, etc., etc. Okay. So we're going, and then so just imagine we collect data for 20 snakes. All right, is this okay? And we're going to graph these. Okay, so we graph these with what's called a scatter plot. Okay, so if you can remember back to algebra, graphing coordinate pairs, do you guys remember how to do that? Mm-hmm. You just go on your x-axis and we'd say, oh, here's 32, 33, 34, 35, 36. This is a terrible, I'm going to run out of spots here. And then over here, I'm going to have, maybe 4.0. So each tick mark being, 4.2, 4.4, 5.6, 5.0. Okay, and we would plot these. So I would say 32 up at 6.2, and so I'd get, kind of a dot right there. And this one is 25 and weighs 5.1 pounds. So maybe a dot right there, and here's 29 and 5.8 and a dot, something like that, okay? So these are the 3 dots. This is Sam, Simon, Sally, okay? And then you can imagine we have more, more snakes. I'm gonna have a total of 20 dots, right? So I'm gonna just add, just pretending that I've gathered more data here. Something like this. So now I'll have 20 dots represented total in our scatter plot. 20 snakes, each with a dot. Okay. Is this representation and creation of a scatter plot okay with everybody? Okay. Yes, good. Okay, and so chapter 4 is all about how do we then describe a scatter plot? Okay, we've got 2 variables. We've got the length and weight. We have 2 numeric variables. Okay, so that is important. If we have a categorical variable, we can't do this. So we have 2 numeric variables. And we create a scatter plot, and we graph all of our data. And then we want to be able to describe this, okay? And so if you had to describe an overall trend or an overall relationship between the length of a snake and the weight of a snake, what would you say?
The longer the snake, heavier the...
Yeah, so a good description would just be, snakes that are longer tend to weigh more. Snakes that are shorter tend to weigh less. Okay? So that seems to make sense. Okay. And so this description describes what we call the direction of a relationship. So let me know when I can flip to the next slide or start a new slide here. We're okay? Okay, so, sorry, the direction of a relationship. And so we have a few ways. We've got positive direction, negative direction. Well, that's really it. But it could also be neither. All right. Okay, so a positive relationship means large values of x. So if I label one variable x and the other variable y, okay, large values of x are associated with large values of y. Okay, and so the example with the snakes would fit this category of a positive relationship, right? Longer snakes, meaning length is large, is associated with heavier snakes, meaning weight is high, okay? And positive also means small x goes with small y. Okay, I should probably write small values of x are associated with small values of y, but I think you catch my drift here. A negative relationship is just the opposite, okay? Large values of x are associated with what? Small values of y. And small values of x, so I'm just going to write small x goes with large y. So large x goes with small x goes with large y. So the positive relationship example would be snake length and weight. Longer snakes tend to weigh more, smaller snakes tend to weigh less. Okay? A negative relationship. So there's different examples here. Perhaps altitude and air pressure. So I don't know if you guys are aware, but if you go up higher, so up to some place like Denver, where you're up high, or Mexico City, where you're on top of a mountain, you have lower air pressure there. Okay? You go lower levels, okay, so small x, you'll have higher air pressure. Okay, and then neither would then be large values of x are associated neither with large or small values of y, okay? And the same goes for small values of x. I'll say ours. So this could be something like GPA and weight. Okay. Do people with high GPAs tend to weigh more or weigh less? Or do people with low GPAs tend to weigh more or weigh less? No, we don't really see a relationship between GPA and weight. Okay. Is that confusing or? Huh?
Grade point average.
Yeah, GPA being grade point average, yeah. So do students with, you know, do 4.0 students, or do they tend to be, you know, way more or way less? No, we can't really. Huh?
It's an interesting concept.
Yeah, we would, the express plan for higher grades would then be a diet plan or a weight gain plan, right? So, no, that's not how it works, so. Yes?
Do they have to do with slope?
Yeah, well, okay, so if we were to make a scatter plot, maybe this is a good little, good thing to include. If I were to make a scatter plot for each of these, so positive, we would tend to see something like this. Negative, we would tend to see something like that. These are, you know, maybe a little too perfect. And then neither, you just see something like that. We cool? All right. Next slide, here it comes. Okay, we can also talk about the strength of a relationship. Okay. And so the strength of a relationship, this gets into the idea of how much spread is there in our data, okay? It's like, how much spread is there? Okay. Or another idea is, how good of a prediction can I make? Okay, so we might see, okay, so something that will have a strong relationship. This means there's little scatter or little spread or scatter. And, you know, if you know X, you can make a good prediction. So probably the snake length and weight would be a good strong relationship. So. The idea being, if we know the length of a snake, can probably make a pretty accurate prediction or its weight. On the other hand, you have a weak relationship. Okay, and that means we have lots of scatter or spread. Okay, knowing X tells you a little bit about Y, but not very much. But not very much, or you know, our predictions will not be very good. I'll say will not be very precise. So maybe an example would be the value of someone's car and their annual income. Okay, so in general, people who drive very expensive cars generally have higher income. People who drive low value cars generally would have lower income. However, do you have people with high income driving low value cars? Sure. Do you have people with low income that might be driving cars that are valued high? Oh, yeah, okay, and so so just seeing someone's car doesn't tell you you can't predict someone's income very well. At least not any more than within, several tens of thousands of dollars, right? Maybe you can ballpark it and say, this person drives a Honda Civic, so I'm going to predict their income is anywhere between it could really be anything, right? If someone drives a Honda Civic, it could be anything. It could be anything between 20 to 100 something thousand. Okay, if you see someone driving a Mercedes-Benz, maybe that narrows it down. But you probably have people between 50 and whatever $1 million driving Mercedes. So it gives you some idea, but it doesn't tell you very much. So this relationship we would say is weak, okay? And so in a strong relationship, if I had to draw a little picture here, you'd have something with kind of just very little scatter, and you got like this very nice line forming. And with a weak relationship, maybe overall there is a general trend going in the positive direction, but you've got a lot of scatter as well. And you can have strong relationships in the negative direction. You can also have weak relationships in the negative direction as well. These pictures here are in the positive direction, and the examples I gave are in the positive direction, but they could apply for both positive and negative directions. You have a question? Or no? No question, okay. Is this all good here? Okay. And another thing that we need to be aware of is the shape or the form of a relationship. So all of the examples I've shown so far have been linear. Okay, so we're just going to classify relationships as linear or nonlinear, and maybe in a more higher level statistics class you would break down the nonlinear ones into specific types. But linear means a straight line can describe the overall trend. And nonlinear means a straight line does not work. And so linear would be something so that works linear because it seems like a straight line could describe our data there. Whereas we can have lots of examples of nonlinear. So nonlinear, you could have something like this, or what's going on? So these would be nonlinear. And in our class, we're only going to learn how to work with linear relationships. Okay. So if we create a scatter plot and it looks nonlinear, then we have to say this is a nonlinear relationship. Our methods won't work. Okay? So far, so good? Yes?
Is non-linear considered negative or neither?
I mean, so you could talk about the overall trend and just say, is big X associated with big or small y, and try to talk about positive or negative in that direction. In that way, so in this case, this would be nonlinear, and we could talk about this being positive trend because as X gets bigger, Y gets bigger. But in this case, you have neither positive nor negative, right? Because over here, it's big X is associated with small y, but so is small x, and it's just the middle values of x that are associated with high values of y. So this would not be neither positive nor negative, okay? And so, but again, you know, we're going to just focus on linear relationships in describing those things, okay? Oops. Okay, so we have a summary statistic to describe the relationship between two numeric variables. Okay. And so this summary statistic is called the correlation coefficient. And the symbol that we use for that is R. It is oftentimes we just might say, we just might call it the correlation rather than using its full name. Okay. And so the correlation assigns a number that tells us the direction and the strength. So the correlation turns that concept of direction and strength into a number. Describe or summarize. The correlation can be calculated for any two numeric variables. However, it only makes sense if the relationship is linear. Okay, and so let's talk about R. So R is always between -1 and +1. Okay, so the sign of R is the direction of the relationship. So if R is positive, then the direction of the relationship is positive. Just a quick check. Don't shout it out, but I want to make sure you guys can think of this. What does it mean for X and Y to have a positive relationship? X and Y to have a positive relationship means, and don't shout out your answer, but think of this answer. Okay? So X and Y having a positive relationship, do you guys have an answer in mind? It means large X is associated with large Y, and small x goes with small y. Okay? Negative relationship is just the opposite. Large X goes with small y, small x goes with large y. And so if R is positive, your relationship is positive. If R is negative, your relationship is negative. Okay? And then the magnitude of R describes the strength. Okay? So if R is, close to 0, like negative 0.2 or 0.15 or something like that, the relationship is weak. Okay, and if R is far from 0, now it can't get that far away because it's always between 1 and negative 1. Okay, so, but something like, 0.9 or negative 0.85, something like that, the relationship is strong. Okay, so let's think of a few examples here. Is this okay? No, go back. Whoops, that's not the thing we want. Where did it go? Here it is. I'll let you finish that. Okay, can I go to the next slide now? All right. Okay, so let's talk about this. Okay, so maybe we're going to look at many different countries. Okay, so our data from many countries. Okay, and for each country, we gather two variables. X will be the life expectancy for men, and then Y will be life expectancy of women. Okay. So what kind of relationship are we going to see here? So, if you look at the United States, the life expectancy for men is probably like 78 years or something like that, and for women it's maybe like 80 years or something. I don't know. It's something around there, okay? I could be wrong, and I apologize if I am. And then you go to, other countries around the world where maybe, they're facing different problems, and you might have life expectancy of men to be maybe 60 years, and life expectancy of women to be 62 years or something around there, depending, okay? So overall, if we looked at many different countries, what kind of relationship do you think we'll see?
Positive.
A positive relationship. And do you think it'll be a strong relationship or a weak relationship? It will be very strong, okay? So, if we do X over here, life expectancy of men, and life expectancy of women, we're going to see some scatter, okay? You're going to have, a few countries where maybe the life expectancy of men is 75 years, And one country where the life expectancy of men is 75 might have a female life expectancy of 75, and another place might have a female life expectancy of 78, and another place might have a female life expectancy of a few more years than that. But you're not going to see a drastic difference between these countries where the male life expectancy is 75. Okay? So you're going to see a very strong relationship, and we will say probably R is something like 0.98, something very close to 1, but not quite. Okay, so strong relationship. So if you know the life expectancy of men, you can get a very good idea of the life expectancy for women. Okay. Okay, so if we know X, we have a very good idea of what Y is. Okay. Here's another thing. We're going to look at data from many different cities. Okay. And an X will be percentage of homes that are smoke-free. Okay, so do not smoke. So no one in the family smokes. So these are smoke-free homes. And then Y will be percentage of smokers who are in high school. Okay, so we're going to go from city to city, and we go, in St. Louis, this percentage of homes are smoke-free, this percentage of smokers are in high school. And then we go to Los Angeles. This percentage of smokers, these percentage of homes in Los Angeles are smoke-free, and this is the percentage of smokers in high school, things like that. Okay, so we're going to go around the country, looking at many different cities. What kind of relationship do you think we'll see? Okay, so if the percentage of homes that do not smoke is high, do you think Y is going to be high or low? Low, okay? And if the percentage of homes that do not smoke is low, we will expect Y to be high. So we're expecting a negative relationship. Do you think the relationship is going to be very strong or not very strong? What do you think? It's a little bit harder to tell, and if we look at the data, we do see a negative relationship indeed. However, there is quite a bit of scatter, okay? So just knowing how many homes don't smoke doesn't tell us too much about what percentage of smokers are in high school. It does tell us there is a relationship where if there are many smoke-free homes, you're not going to have very many high school smokers, but overall the relationship looks, it's kind of, there's a good amount of scatter, okay? So it's not the best predictor of of this. And here we have something like r equal to negative 0.6. Okay, so we have this would just be what we might say a moderate relationship. And it's negative. Okay, so knowing x gives us an idea of y. But does not tell us everything. Is that okay? All right. Why don't we take a break here, and then we'll talk about modeling relationships when we get back.